now up to the last short course. I will make an educated guess that there is probably nobody in this room who doesn't know who Mike Watkins is. Since we're moving to the living legend category, I'll be brief. Mike was, of course, for very many years at JPL. He managed, as a mission manager, the Mars Science Laboratory mission with Curiosity rover deposited on Mars. Then he originated the concept for the GRACE mission, GRACE follow-on, GRAIL. He acted on those. He went through a whole bunch of executive posts at JPL up to having served as a director for 5 years and eventually moving to Caltech as a professor here. And he's a fellow at JPL, a number of organizations, and a very famous man, and it's a pleasure to leave him on stage.
Thank you. It's great. Thanks to all the organizers for inviting me to this. It's a chance to meet a lot of old friends. There are at least 2 people in this room that I've known for over 40 years. So I'm not that old, so it's pretty good. And there's probably 5 more that I've known for 30 years. And I did my PhD dissertation on satellite laser ranging to LAGEOS. So there's a lot of old history here that I have to try to remember, actually. But originally, I think this talk was called The Future of Solar System Science with ILTN. And then sort of along the same lines that all of us have realized this morning is we don't know what the future of solar system science is yet, because we're still trying to understand what can this really bring to the table and what architecture is needed to optimize that science. What I thought would be actually more useful is talk about how we got to where we are and the present state of solar system science, because a lot of ILTN has to battle the same demons, right? A lot of what we've been doing is sort of a ground-based kind of a small version of what ILTN might be able to achieve. And of course, that's the DSN. I'll talk more about that. But that causes me to have to indicate some thanks to the Solar System Dynamics Group at JPL. The supervisor is now Ryan Park. I see my old friend Paul Chodas there. This is an amazing group. Some of you that go way back might remember Don Yeomans ran this group for a long time. They're one of the only people in the world that do solar system science through planetary ephemerides. And they're amazing at what they do. And based on my history, I can never stop talking about how cool JPL is. But it's also in the navigation and mission design section, which I was in for a number of years, and also a fantastic section. Making the ephemeris and then use that ephemeris to deliver satellites to the proper targets. And before that, I was in the tracking system section. In fact, Andrea and I started in the same group in tracking systems. This sort of, I have 2 slides here that speak to everybody's talk before me, I think. So let's start with planetary ephemeris. I said these words already. Obviously the DSN has been doing this. It does it in a funny way, right? It does it the same way ILTN does, which it does it by tracking spacecraft orbiting the other planets for the most part. There's a few exceptions to that, but that means a lot of the capability is really in the geometry and the measurements that ILTN could bring. Okay, so planetary ephemeris, it provides position and velocity of the sun, the planets, and the moon, and Pluto, and a few other objects, Ceres, Vesta, and also computes orientation, particularly of the moon, and partly because we have some reflectors on the moon. It really serves as the foundation for studying dynamics of the solar system. So if you want to look at orbit prediction, look at the near-Earth objects, are they going to hit the Earth or not? What can we learn about planetary science, and how can we put all this together into a coherent story about the solar system? This ephemeris is pretty much unique to JPL. I think there are a few special purpose people doing ephemerides. We saw the study mentioning the bounds on where Planet 9 could be. That was kind of special purpose ephemeris study. But pretty much every organization in the world uses this planetary ephemeris from JPL. And that includes all of our foreign partner organizations. None of them have spun up an operation quite as significant as what's going on between the DSN and Solar System Dynamics Group. And you can all go online and download it, and people do it all the time. Now, Jacob's been doing this for a long time, right? Because as soon as what's the first thing you need when you go somewhere? You need a map, right? So you gotta have a map of where you are and where you're going. And this is a slide of how accurate that map has to be. And in this case, it was kind of driven by Mars landers. So this is an example just for Mars. We could make one for some other planets as well. But Mars landers, they want to land in a certain place on Mars, right? So they've got to enter the atmosphere at just the right place. And you have to know where that place is, both in an optical frame as well as in a radio frame. And the precisions for those have gotten tighter and tighter and tighter. And you see back in the days of an orbiter, if you're going to go into an orbit that's 500 kilometers altitude, you only have to know Mars to 100 kilometers or so, right? But if you want to land, and you want to land within meters, suddenly the accuracy that you need from Mars is dropping way down. So in this case, for sample return, 2020 was a few hundred meters, and sample return can be even less than that. And we think we can meet that, and I'll show that in a minute. So how do we compute it? So as I mentioned, we track spacecraft. There's a few cases where we use some other data, particularly if you don't have a spacecraft at that planet, for example, the outer planets. You could do stellar occultations, for example. In some rare cases, they can actually use older eclipse data to try to get very long-term orbits for the moon in particular. But basically what we do is we track spacecraft. And the only exception to this, as Evan mentioned, is the Apollo astronauts left some laser retroreflectors on the surface of the moon. And we track those, and that gives us incredible accuracy on the lunar ephemerides. So what we do is, so certainly recently, the last 20 years is completely dominated by DSN tracking of orbiters. In most cases, it's Doppler and range, so direct tracking to the spacecraft. In some cases, we do interferometry, so we actually look at positioning the spacecraft with respect to the quasars, or with respect to an incoming spacecraft with respect to an orbiting spacecraft. And what that gives you is range directly between me and you, but also you need some way to know, well, where am I in the plane of sky? And the interferometry data gives you the plane of sky information for the most part. Right, it's one of the problems with navigation and orbit determination is if you only have line of sight Doppler, right, you can have almost the same line of sight Doppler here, or you can be here and have almost the same line of sight. So getting that plane of sky measurement through interferometry is a critical thing to do. And you'll see, by the way, that that's also limiting in terms of the 3D accuracy. Now, since these are microwaves, right, and not lasers, so they've got to go through the Earth's atmosphere, the Earth's ionosphere, interplanetary plasma, and then get to the spacecraft, and then come back through those same errors. We used to use S-band for the most part. Now we use X-band for almost everything. There have been a few demos with Ka-band. There's only one Ka-band uplink right now, DSS 25. One of the advantages, if you have X and K together simultaneously, then you can remove a lot of the ionosphere and interplanetary plasma. It's rarely done, very rarely done. Here's an example of how much that tracking has improved over time. This is a little bit of outdated. It's a little bit notional too, but sort of how well could we navigate a spacecraft or do orbit determination on the spacecraft? So this is Mariner 2. It's the first interplanetary spacecraft that we launched. It's actually mentioned, by the way, in President Kennedy's speech of why we go to the moon. He actually says in that speech, no one quotes this part of it, that we have a spacecraft on the way to Venus right now. And that's Mariner 2. And you can see that we used only Doppler, S-band Doppler, then range was introduced, then some VLBI with increasing spread of the frequency range of the tones and wideband recording, and then eventually some more advanced interferometry. But you can see we've gotten so we could only navigate a spacecraft to maybe 1,000 kilometers or something like that. And in this case, this is in nanorad, so it's 1 nanoradian is 150 meters. So this is 150 meters here. So you see we've gotten all the way down here to where we're doing spacecraft orbit determination, deep in the solar system at sort of the meter level or few meter level. Okay, I think I talked about this already. We calibrate the troposphere and the ionosphere as best we can using GPS, right? So, GPS is pretty good at sensing the ionosphere, and we can also use GPS solutions for the troposphere. In some cases, we use a water vapor radiometer at the DSN sites as well. Solar plasma, you can do phase versus group delay, but what you mostly do is hope that you're not passing the radio signals very close to the sun. So this is an example of what we call the Sun-Earth probe line. So here's the sun, here's the Earth, and here's the spacecraft. So if this line here gets close to the sun, then you're getting more and more plasma delays. Of course, when you're in opposition the other way, then everything's much more quiet. So here's an example of sort of noise created by different sources. So this is plasma at S band, this is plasma at X band, plasma at Ka band is one of the reasons to go to Ka. On the other hand, your sensitivity to the atmosphere goes up in Ka band. And this is an example, for example, summer troposphere. This is at Goldstone, for example, when it's pretty dry. And these are RMS fits to the data for some Mars missions as a function of this SEP angle. And this is in millimeters per second. And so you can see actually sometimes up around 1/10 of a millimeter per second, even higher, can actually go all the way down to something like 0.03 millimeters per second, so or like 30 microns per second. So this is a pretty good measurement type. It's something to keep in mind when we talk about what we're going to get out of switching to a laser frame. And then the ranging, as I mentioned, is the line of sight ranging again, is something like 2 to 10 meters. So when we take that tracking data, we fit it into an ephemeris, what happens? So here's one-way range to Mars. So we can fit this data to about a meter. So this is, we're tracking MRO or Odyssey or MGS. We fit the data, and again, there's some noisy periods because of plasma and other things, but we generally fit this data to about a meter for the spacecraft. And then this is the plane of sky measurements I talked about, the interferometry data. And so this is actually a quarter of a milliarc second, so it's about 200 or 300 meters. So imagine the error ellipse or the error sphere around the spacecraft. It's really just like a pancake, right? So it's a very, very thin error ellipse in the line of sight, but it's kind of broad in the plane of sky dimensions. So we put that into an ephemeris, and then we try to predict how well it's going to fit the data. Okay, so this is data fit to Mars, fit to a spacecraft orbiting Mars, and you see it fits very well, right? So this is that 1 meter fit, and then we have to terminate that and deliver it to the navigators to use. So in this case, this is for Mars 2020. They made a delivery in June of 2020, right? And so through the fit interval, the ephemeris was pretty much perfect, right? So it fits the data perfectly. Range prediction is something like 15 meters. And then range fit was about 1 meter. The prediction turns out to be accurate to about 15 meters. So that's this noise here is the ephemeris not being accurate, right? So after I stop the fit interval and have to predict the ephemeris forward, you start to see these errors, exactly as Konstantin was talking about, right? That's errors in asteroid masses, right? So we don't individually know the mass of every single asteroid and track every single asteroid in this fit. So you have to kind of guess which ones are going to be, do the best you can in the fit. And this is an example of the thousands and thousands of asteroids that we don't have. So the angular precision, right, the plane of sky, rather than being 15 meters, is something like 200 meters. That's not because the asteroids are worse in plane of sky, it's because the measurements are not quite as good. Right, so you're still stuck in this case by the actual interferometry measurement. And so you can't see the asteroid perturbations. This is still a problem, by the way. You know, if we had even better tracking, this error would still be there, right? So if I had laser tracking to 1 millimeter and I delivered the ephemera, so all of this fit would have been 1 millimeter instead of 1 meter, but you still have the problem of the physical model of the asteroid masses is not good enough. So that's one thing to pay attention to on ILTN and in the architecture that we start to explore is, you know, what can I do about systematic errors that are not related to the measurement system? Okay, let's switch to the moon. So the moon, we can cheat a little bit because of these retroreflectors that the astronauts, and I think there's a Russian robotic lander also as well. And so you can see the laser ranging. This is what Evan talked about, ranging to the moon. This, you know, was something like a meter back in the 70s, and it's gone all the way down to 1 centimeter now. So we actually get 1 centimeter ranging to the moon, which is pretty amazing. And of course, you know, that may actually be used soon, right? You know, astronauts or advanced robotic probes may actually want this kind of accuracy for the moon. If you sort of switch your field of interest, as Andy was talking about, and you say, well, rather than just looking at the ephemeris and how well I can deliver, what have I actually learned about the interior of the planets using DSN data, and then also using whatever other instruments happen to be on the spacecraft. So if the spacecraft, for example, had spacecraft-to-spacecraft ranging, like GRACE or GRAIL, or if it had an altimeter to measure topography. You can actually learn a heck of a lot about it. Now, I actually don't really mention GRACE in here, strangely enough for me, because GRACE is another example where the time variable mass of the Earth, mass distribution of the Earth, due to climate and due to weather and due to you know, other Newtonian phenomena, completely dwarfs the measurement noise and any physics. People ask me a lot, as Kirk was saying, you know, we actually do nanometer per second measurements between the spacecraft with GRACE. And people always ask me, well, can't you do a relativity thing? Can't you know, find interesting things about solar system physics using nanometer per second data? And the answer is no, because there's just this huge amount of the fact that there was a storm, you know, over the Gulf of you know, Alaska at some time, or there was extra melt season in Greenland or something like that. All of that noise is a problem. And that's going to be a problem also, again, for ILTN. So anytime you don't understand the physics that are driving you, and that physics is a noise source to you, then that actually limits how much you're going to get out of the improved measurement precision. So the example I'll give is not GRACE, but GRAIL, where, you know, GRAIL has no atmosphere, has virtually no ionosphere. We could fly very low over the moon, and so we get a fantastic physical measurement of the moon's you know, own gravity field without these external perturbations. So we actually use Ka band between the two GRAIL spacecraft. We used S-band to the Earth. We also had an X-band radio beacon that we added. This was a normal DSN S-band tracking, and this is a special X-band tracking that we had, partly to help with the clocks. And that resulted in a really nice gravity field. This, for anyone who looks at gravity fields, this is an amazing thing. This is a post-GRAIL gravity field. You can actually see, you know, the few kilometer scale features here. And you can see some areas where, in particular, where the altitude is a little bit higher over various parts of the moon than it was on the far side. This is an example of the topography and the gravity field. So this is LOLA, Lunar Laser Altimetry Topography Field, and then this is the GRAIL gravity field. And I think this is the only time in history that these have been about the same wavelength of sensitivity. And what that enables you to do, right, is to say, well, okay, so this feature that I see in the topography, how is it reflected in the gravity field? You know, did the crust accommodate it? You know, or is it you know, in equilibrium with the crust below it, with the mantle below it, or is it standing up at some level? And that tells you a lot about the interior structure of the planet, and also maybe how fast did it cool? Like when this feature, an impact feature was formed, did it have a lot of time to compensate or not? And so there have been many papers written on on the structure of this using the combination of topography and gravity. And Mars has similar, but not at this level of precision. So here's an example of how good the current gravity field is, a degree 1500. So that's a gravity half wavelength of less than 4 kilometers. That's pretty amazing. And here's an example of how well you can fit the data with tracking data. So here's an example of fits using degree 900, degree 1200, and degree 1500. You can see how much it's sort of improved over time. And here's an example between showing the 12 and 1500, showing that going to higher degree actually reduces the fit RMS. So that means when the spacecraft is flying over a crater that wasn't resolved in the degree 1200 field, harmonic degree 1200 field, it is resolved in the degree 1500, and the orbit gets much better. Now, what's interesting about this is the discussion we just had at the end of the last talk during the Q&A session, which is what altitude do you want to be at for ILTN? So this would make you say, I don't want to be particularly low because I'll have to have incredibly good knowledge of the gravity field in order to get the orbit precision that you need to do the kind of studies we're talking about, right? On the other hand, if you're too far away, you lose the gravitational tie to the center of mass of the planet, right? Because you're using the orbit as a proxy for the center of mass of the planet. So that's a trade study we need to actually do. It's complicated a little bit by the farther away from the planet you are, the more likely you're going to be visible to the other ILTN components. You're real low, you're going to be eclipsing a lot. So that's a trade that's certainly worth pursuing. Okay, so let's look a little bit about the future here. A lot of this has been said already, so there's no need to really belabor it. We will continue to improve dynamical modeling, continue to improve our ability to remove the ionosphere and the solar plasma and all of these things that we're currently doing. And you get a little better at that all the time. You get a better model of the atmosphere, a better model of the ionosphere, better model of the spacecraft and how it's thrusting and attitude control and all of that. But we're starting to get asymptotic, right? Because the measurements can't improve that much more from where we are in the microwave domain. And the spacecraft modeling probably can't improve much either, right? You can fly a drag-free spacecraft maybe, which could be considered for ILTN. But basically, when you look at all the systematic errors, then I think we're kind of getting asymptotic here. So what does ILTN do to help remove that? It removes almost all of the data noise components. You can drive all of those microwave noises down virtually to zero. But you also add this geometry, which I think helps, right? So you're not always just looking from the Earth. This ability to look simultaneously from the other bodies. We also think we need to look at what's the optimal observing strategy. At what point do I switch between planets that are observable and how long do I track for them, things like that. But so I think, and we have to quantify this, I think the combination of improved data noise and improved geometry by doing planetary to planetary measurements, I think are a key aspect of ILTN. But it's still stuck with the fact that those spacecraft that we're ranging to have their own intrinsic errors in the orbit determination. So again, maybe you want to think about them being drag-free. Maybe you want to think about them being like being two graces or grails. And then if you want to infer, so suppose I have ILTN, I've made measurements between Mars and Venus, and I've tried to get an orbit, and I want to then infer, well, what was causing that? There's some interesting thing causing that orbit. Well, you're still stuck with removing some of the things that you're not interested in. So if you're interested in gravity waves, or you're interested in dark matter or something like that, you've got to make sure that you get out of the type of error that's in things like asteroid perturbations. I think more detailed simulations are very important here. One of the things that helped us a lot with GRAIL and GRACE was that it's a very physics-based problem. Right, so Andrea mentioned, it's hard to do plant biology, right, and do a quantitative simulation of what you're going to get out of a mission that measures plants. In this case, we kind of know, right? We can actually simulate very well the physics and the measurements. It can actually say, yes, I will have this sensitivity to measuring G. Yes, I'll have the sensitivity to measuring planet 9. We can actually quantitatively bound those. The simulations can be kind of complex. I think we heard from Constantine that we're at a state where we can computationally manage those. I think that's one of the things we should do. And when you do this, you answer a lot of the questions that reviewers have, like, well, is your thing really going to work? Like, how do I really know what you're going to get out of this scientifically? Are you going to actually fill out and meet your science traceability matrix? And the answer is yes. For these kind of missions, we really can. And that's a big advantage. For the interplanets, are we going to, without ILTN, that Bepi Colombo has just kind of arrived there. We have some Venus radar missions that will get topography. We have proposed GRACE at Mars a couple of times, but it does not look like it's on the horizon. And so I think without ILTN, we're not going to see much more of that. And then, obviously, search for, Planet 9. Probably cannot do it, as you saw from Constantine's talk. Search for gravity waves, which actually was tried with Cassini. Maybe look for dark matter, other exotic physics. So, obviously, ILTN is a potential. Like I mentioned, I think it's the only real proposed significant improvement in solar system measurements, and I think we need to do some simulations. Thanks.